So just a reminder, it's fine to people can participate in sampling if they like. As I mentioned last week, I was unaware that there'd be a charge that would kick in, and otherwise I would have talked about it at the beginning of the semester with you all, that there was a charge associated with it, and I thought it was still an experimental thing in this course, and we were still developing it with that company, but they decided to implement a charge, not even giving us fair warning. They said they gave us fair warning, but they didn't. They tried to pull a fast one. So I decided to pull the plug on them for that, mainly the lack of communication. It was maybe in the future another professor might implement sampling. So just turn in the sheets at the back of the pre-lab sheets, and we will grade those like we normally did. Please, if you're having trouble with any of the calculations, please contact your GSI about those pre-lab calculations, because those are really important for being able to do your your experiments. You don't want to weigh out like 10 times more than what you need. Of course, hopefully the GSI won't let you do that. All right. So last time I was sort of in a rush because I talked too quickly, and I want to talk about when we use particular indicators in the laboratory, and that depends on the type of acid-base titration you're trying to accomplish. And so I'm going to go through 3 different cases. I think there's a few cases that are in the lab manual as well, and so you can compare and contrast what I'm talking about with what's in the lab manual. And certain times certain indicators work, and other times they don't. And so just to get us back on the same page, we talked about having, say, a pH scale on the y-axis, and on the x-axis here, we're just going to have different indicators, like strips drawn for each of these indicators. I don't know if you all have access to colored pencils or whatever, but you can just shade on either end. You'll get the same idea, and you can look at my notes. I'll PDF copy on the web. Okay, so we talked about that should be litmus. Litmus, which isn't typically used in titrations, but I'm putting it there since it's a standby that everyone knows about. Methyl orange, which is pK is around 5, and then phenolphthalein. pKa of this guy is up in the basic range around 9. And they all have different colors and different transition points from which they change from one color to another. So if you're familiar with litmus, you know under basic conditions it's much more intensely blue, and as you approach neutral pH, it becomes light blue to dim, and then you get to the reddish, pinkish regime, and then under much more acidic conditions it's intensely red. And so it's a nice indicator right around pH 7. There's a nice transition between red and blue, high contrast colors, easy to use. And then there's methyl orange, which we talked about in some detail, which is very yellow when it's deprotonated, and then around pH 5, it becomes, color maybe deep orange. You might mistake it for red orange. I got in trouble, I say trouble jokingly, calling it reddish, more reddish than orange, but there it is. And, you'll have a gradation of color there between orange, light orange, and yellow as you go through that plus or minus, say, 0.8 units away from that pKa. Then we have phenolphthalein. We need a pretty color here for that. Phenolphthalein is like a deep magenta, fuchsia color when it is deprotonated, okay? And then, it transitions out to a lighter pink and then colorless, okay? So I will indicate that as colorless when it's protonated below, at pH is below the pKa, and then it's deep magenta here. For people that don't see colors the same way, I'm going to mark the colors here this way. Some of us are colorblind and are not able to see colors very well. Okay, so those are the color ranges, the colors, the pH ranges. They're all related to the pKas of these dyes. These are simple dyes that only have 1 pKa. Someone cleverly found a previous dye that had 2 pKas, so that would have actually 3 colors. All right, but we're just keeping it simple here. So that covers a variety of ranges, and we can use those in an acid-base titration. And as I said on the top of the slide, we're going to do a titration as you perform in the laboratory if you haven't done so already this week. And you're recording on the y-axis pH, and on the x-axis you're titrating a volume of acid. So you say on the x-axis volume of acid added or titrated. You can say titrated here if you want. And that's usually in units of milliliters. Your apparatus counts drops and then converts that to milliliters because you did a calibration. So in red here, I'll draw what I imagine the titration curve will look like. Again, I'm going to label this graph as a strong acid versus a strong base, okay? This is the case we're talking about. And remember that the strong acid is listed first, so that is what we call the titrant. And the titrant, if you look at your titration apparatus, has some burette or reservoir here, and that is where the titrant resides. That's what you titrate into your beaker on your stir plate thingy with your stir bar in it, and hopefully you have a pH probe in there, and so forth and so on. We yet make it even more complicated and have this magic device here called a drop counter. Anybody have trouble with drop counter? Yes, sorry. There are some drop counter issues, and hopefully they'll be worked out for next time. If you have trouble with your drop counter, you just get a new one in the storeroom, okay? Sometimes they're not fixed or functioning well. So there you go. You have your drop counter, your pH probe. Anyway, the point of this drawing is to say the titrant goes into the reaction vessel. So let's go back to our graph. And in red here, you start out, because remember you have a strong base, it's in the vessel, so the pH is going to be high. Let's say it's pH, 1 molar base. And then suddenly when you start to hit the transition point, that'll occur somewhere, the equivalence point will occur somewhere around pH 7 for a strong acid versus a strong base, generally speaking. Because basically you're looking there at the pK of water. And so this is your curve. So now you want to say, well, what dye would be the best dye to use? And as I was querying the class here, people that might have had drop counter issues, you may have more subtle drop counting issues. Let's say this is every 5th drop, okay? And you would have done a calculation beforehand. That's why we do pre-labs, to say, well, how much volume of acid would it take to neutralize my base? And if you were off by a lot, and looking at what the drop counter is telling you versus what your pH indicator is telling you, you'd say, oh, I flubbed that experiment. Those data are no good. That is a reason why we have both the pH indicator and the drop counter in there at the same time. So let's think. We're not going to worry about litmus because obviously you could choose litmus. It's pretty nice for this experiment, but people don't use that. It's not really a dye that's typically used. But let's consider the 2 other dyes. One is phenolphthalein, which we say goes through its transition somewhere around pKa of 9. So that's phenolphthalein indicator. Okay, that transition point pKa is about 9. Now, you're saying, well, you might say that endpoint would be premature to the midpoint, okay, the titration equivalence point here. And that would be if you were really looking at the middle of that range of fuchsia colors that would be produced as you went from the darkest fuchsia down to the lightest. And really what you want to do is you want to imagine making your endpoint here where the faintest amount of dye is detectable by eye. So this is where you want to pick your endpoint. I'm sorry, I had to squeeze that in there in small print. But the endpoint is going to be, that endpoint is detectable by eye at 0.8 pH units below the pKa. So that puts you around 8.2. You're only 1.2 units off the pKa, off the equivalence point. And because it takes very little volume of acid to move quite a distance in pH, look at how steeply this is moving on the y-axis, you will not have much experimental error with that measurement. And phenolphthalein is a good, it's a good indicator choice in this application. So we give it the pink check mark. Now we can think about another option here, which is the methyl orange. And the methyl orange is going to happen sort of on the opposite end of the spectrum here. But it will actually turn out to be pretty darn good too. And so here's your yellow range here, and then suddenly you transition. And that transition point would be, around a pKa of about 5. And so again, in a slightly different way, you'd want to sense when you got rid of the slightest hint of orange color. And that would be around pH 5.8. You'd only be 1.2 units away from pH 7. And again, great choice, right? So you want to pick your titration endpoint here. This is where you want to set your endpoint about, plus 0.8 units. This endpoint you want to make, say, minus 0.8 units. Anyway, that's what you can detect by eye, and either would work out. They're both good answers on an exam question. The subtlety there is that you want to work on the right bleeding edge of that indicator. Okay, so that's the easiest case there: strong acid, weak base, and there's obviously other cases to consider. For example, you could have in there instead of a strong base a weak base, and so weak base will perhaps the pKa of the weak base is around 9, 8.5, and if that's the case, then you're not going to be in good shape if you try to use certain indicators. So again, same kind of graph here that we would measure in the laboratory with volume, pH on the y-axis and volume of acid added on the x-axis. And instead of starting out at pH 14, now you have this weak acid, say its pKa is around 8 or something like that, or 9. And so you start out somewhere in there, and then you would titrate through the equivalence point, and then come down, say, to pH 0 if using 1 molar, pH 1, pH 0, depending on the concentration of the acid you're using, your strong acid. So you have your equivalence point there. No surprises about the equivalence point. But the one surprise that you'll have here is that you can't use, and you may not be surprised if you knew a lot about weak bases, but this phenolphthalein indicator is not going to work out for you. Because phenolphthalein is going to be, the color change is going to be happening either prematurely before you start your titration, or maybe during this titration of the weak base, or it's already happened because the weak base has a lower pKa than phenolphthalein. So phenolphthalein is a poor choice. Just you couldn't work with it. And because I've limited the cases here, you say, well, of course you know the answer. The answer would be to use methyl orange. And you can see that's going to be quite obviously a good choice because it's almost a perfect choice in this particular application, because right around its pKa you're going to have the equivalence point. Again, probably in this case, your equivalence point will be pretty close to 7. I know it doesn't look like that here, but probably more than likely that'll be close to your equivalence point. And so methyl orange would be a great choice. Oops, I don't want to do it in yellow if I don't have to. It's hard to see. So methyl orange is an excellent choice. So that should be pretty obvious, and you really got to think about, well, weak base, what's the pKa of the weak base, and if I have an indicator that's titrating in that range, not going to be good, not going to be good at all. So now I'll try weak acid versus a strong base. Same kind of graph. Probably could put those both on the same page, but volume of acid added versus pH again. And here's our curve. So we're using a weak acid now, and we have something like, say, sodium hydroxide in there as a strong base. So we're going to start out at high pH, okay, around 14. Then we'll go through a titration midpoint. But because it's a weak acid, it will not get to low pHs, okay? And that's because the negatively charged form of that weak acid, say it's acetic acid or something like that, has appreciable affinity for protons. So because it has appreciable affinity for protons, it's not going to give those up to the pH meter and the solution, and so that the proton concentration is never going to get very low. So you can see that now, well, you have your equivalence point somewhere in there, and obviously the best choice here is going to be phenolphthalein, because that's going to titrate appropriately in this experiment. You start at high pHs, you'll transition right through pH 9 quite nicely, and hit the equivalence point. Okay. So phenolphthalein is the good choice, and because you're working with a weak acid, which may be on the pKa range of methyl orange, most likely the case, since methyl orange's pKa is down in that region, somewhere down in here. And by the time you see appreciable color change, in this case, you're going to be you're going to be well past the equivalence point, and so your titration endpoint is going to be bad, and you're going to have a significant experimental error. I mean, for this dye, you might have this volume. This is your volume of experimental error, and that's not tolerable. Whereas with this dye, you're going to have a much smaller experimental error, probably even much smaller than that, in using phenolphthalein. So methyl orange, methyl orange is a poor choice. So there's a pretty good rule of thumb in this, in that you need to think about the pKa of the indicator and the pKa of the acid, weak, strong acid, weak base, strong base, using the experiment. And so those are the main considerations. All right, so now that's one aspect of the lab that you're working on. Another aspect of the lab, which come to my attention, has been a little bit rocky for certain students, I thought I'd just review it, is in thinking about the hydrolysis of your PET plastic and the stoichiometry in that reaction, which is a little bit more complicated than say, another type of plastic that we talk about, PLA, polylactic acid. So right here is my structure here of PET plastic. And remember that we have PET, the P means poly, the E means ethylene, and the T means terephthalate. So there's both an ethylene group and a terephthalate group in this plastic. And hopefully by now you've drawn the terephthalic acid, terephthalate so many times you're pretty comfortable with it. And then the ethylene group here is in between two carbons. And then you'll connect that out to your ethylene, and then that will repeat, because that other side of the ethylene will connect to the next terephthalate. Okay? So over here, not shown, would be that oxygen from that ethylene if you were to continue this polymer out infinitely. So this is a repeating group, and we don't include that in the notation. So this is a repeating unit. If you were going to draw a polymer, you just cut and paste this and make an infinite chain or a very long chain. Now we're going to do a hydrolysis reaction. So remember that this means hydrolysis, is water lysis or cleavage. And so we need, and the question really is, well, how many waters would it take to break this guy up into its component pieces? And the thing you need to look for in hydrolysis reactions are how many esters or amide bonds need to be cleaved. In this particular plastic, you have ester bonds. Remember, I did an example on Kevlar, which is another case of hydrolysis, where hydrolysis can occur. And those have amide bonds in them. Those are also can be cleaved in the case of Kevlar. I'm sure someone picked Kevlar to do in their report, or maybe not. That might have been kind of almost cheating, since I did in class. But in any case, that plastic can be hydrolyzed also. And so how many waters does it take? Well, you need to look for the ester groups. And this is an ester group here. I'll put a green outline around the ester group. So there's one ester group. And then this is the other ester group. You might think it's hidden. But remember, implicitly there is that oxygen. So this is the other ester group. That's ester group 2. So I'll put a key down here. Those are your ester groups. So that means you need 2 waters, 2 ester groups, 2 waters per monomer, per repeating units in this plastic PET. So the other thing we need to do in a stoichiometry calculation to figure out, and ultimately our question is, how much plastic do we need to get 25 millimoles of ester linkages? And so there's 2 key pieces of information you need. Number of ester linkages, which relates to the number of waters, that's 2. We can write that down. And the other thing we need is a molecular mass. So we've got to go back to our structure to get our molecular mass. And so the first thing that you count are your carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's C10. And because I have all the luxury of these colors, and I can do another color. Now the hydrogens, now you can't see the hydrogens. So it takes a little bit of organic chemistry. You need to look at all the positions where there's less than 4 bonds to carbon. This guy has 1, 2, 3, 4. There's no hydrogens on carbon 1. On carbon 2, you have 1, 2, 3, 4, no hydrogens. But carbon 3, we have a hydrogen. Carbon 4, carbon 7, carbon 6. And none on 8, H just like carbon 1, but 9 has 2, okay? So this would be 5 and 6, and then 7 and 8. So those are your hydrogens, C8, and then we can do oxygens in red. Oxygens are easy to count because they're explicitly revealed in the structure. Oxygen 4. Now who could do the molecular mass of that really quickly in their head? Any savants in here? So carbon, 12, so that's 120. 8 for hydrogen, and then 4 times 16. Does anybody know that one? 64. Add them up, 192, okay? It's kind of a fun number, all right? 192 grams per mole. Don't forget your units. So now we just have to do some factor labeling to figure this out. And so we start out with our 25 millimole, and I'm not going to do it that way because I'm sorry. We start with 25 millimole, 25 times 10 to the minus 3 mole. And then we just do this giant factor label here. And that's mole of ester. Okay, that's not mole of plastic, that's mole of ester. So we immediately need to do a conversion here to mole of PET. Well, that's easy. So mole of PET is in a 1 to 2 ratio with mole of ester. Remember, there's 2 ester linkages per repeating unit in the plastic. Okay? And then we need a molecular mass, 192 grams of PET plastic per mole of PET plastic. And then I made my factor label here thing too long. I can erase it. And then we just multiply all that out. And I don't expect anybody to do that in their head, but it turns out it's around 2.4 grams of PET plastic. That's the answer. So it's not a hard problem once you set it up and you think about it for a while. You only have 2 factors in this factor label, but the trick is first, in dealing with this stoichiometry, the number of esters in the repeating unit, and that really requires you to look at the structure here